Hello students. Today we will start with the discrete time Fourier series properties, that is the DTFS properties. Starting with the first property, which is the linearity property, which says that if you are having two signals x of n and y of n, each having a periodicity of n naught. So always remember, I am not writing that explicitly, but it is always there that xn has a periodicity of xn has a periodicity of n naught. Similarly, yn also has a periodicity of n naught. This is what we are assuming. Okay. So linearity property says that if you are having two signals x of n, y of n, which you multiply it with a constant a and b, then it's as good as adding and multiplying the constant with the Fourier series DTFS of x of n and y of n. Let us prove this. We know the equation of DTFS is 1 by n naught summation within the period n naught multiplied with xn multiplied with e raised to power minus jk omega naught n, where omega naught we all know is 2 pi by capital N naught. Now if I want to take the DTFS of this one, the same equation I can rewrite by writing it as, so as you can see, I have replaced, instead of x of n, I have written this equation. Now this I can split it up into two parts, one for axn and the second one for bxn. Then I will write this is equal to 1 by n naught, which is common, and then summation n for the period n naught ax of n e raised to power minus j k omega naught n, plus then the second part is b y of n multiplied with e raised to power minus j k omega naught n. Now this I can split it up for the two parts. That means I will split the summation for this one as well as this one and take the constants a and b out of the summation. So let me rewrite it as, so I take 1 by n naught common, and then a I take outside, summation n is equal to magnitude of within the range n naught, what remains is x of n e raised to power minus j k omega naught n, plus 1 by n naught is common for both, so 1 by n naught into b summation n for the range of n naught y of n e raised to power minus j k omega naught n. The first part, that means 1 by n naught, and this summation is basically the discrete time Fourier series of x of n, which we will write as x of k, and since we are multiplying it with a, capital A is the constant, and the second part b multiplied with the DTFS of y of n, which is the second part, so that I will write it as y of k. Hence it is proved. So we have proved this particular statement, the linearity property. Next, time shifting property. The time shifting property is given by, if you are having a function x of n, a periodic function x of n, and suppose if you are going to shift it by a value of small n naught, then it's as good as multiplying the Fourier transform of x of n with e raised to power minus jk omega naught n naught, small n naught. You should note here that it is small n naught and not capital N naught. Okay, so let us prove this. The proof again is simple. We write the equation of DTFS and we know that the equation is 1 by n naught, which is the periodicity, summation n is equal to within the period n naught. Now here, just for the sake of trying to make you understand, I will write the summation limit as we used to write in the main equation. Mainly I want to explain something to you here. Multiplied with the function x of n minus small n naught e raised to power minus j k omega naught n. Okay, now we are going to substitute, or I will say put n minus n naught is equal to n1. When I say this, then I can say that therefore I have to put the limit also. I have to find out the limit for n1. If n0 has a lower limit of 0 and an upper limit of n0 minus 1, I need to find out what is the limit of n1. Okay, so that is what I am trying to do here. So if this is the equation, then I can say that therefore at n is equal to 0, which is the lower limit, if I substitute in this equation the value of n1 according to this equation, if you look according to this equation, its value of n1 will come out to be n is equal to 0 minus n0, and at n is equal to the upper limit, that is capital N0 minus 1. If I substitute that value here, I will get the value of n1 as n0 minus 1, which is the value of n, minus small n0. Okay, minus small n0. This one would come as minus n0, sorry. Now if you would look at what is the gap between these two values, this one and this one, you will find out that the gap is again n0 itself. So again, it's as good as writing that whatever be the limit it has changed, the value is basically going to be the same. You are going to take the same period. So it does not matter much in that respect. So from now onwards, I will not write this. I will just straight away say that if there is a summation whose period is n0, after this kind of a substitution also the period will remain same within n0. Okay, why? Because even if I change the values, the limit changes, but the difference between them, yet it is n0 itself. So now I will rewrite the above equation as 1 by n0 summation n is within the period n0 x of, now n minus n0 I will substitute it as n1 e raised to power minus j k omega naught n. Now n I will substitute from this equation, it will come out as n1 plus n0. Am I correct? So based on this, I can rewrite this equation as 1 by n0 summation n within the period capital N0 x of n1 e raised to power, so let me take this n0 part, so e raised to power minus j k omega naught n0, then the remaining portion which is e raised to power minus j k omega naught n1. So here I forgot to write one thing, this limit has to be now n1. Okay, so n1. So now see here, this summation is with respect to n1, x of this is with respect to n1, this is also with respect to n1. So in a way this is basically the Fourier transform, the DTFS of this function. Am I correct? The remaining portion all is as you see in a DTFS equation, correct? So it is basically the DTFS of this equation. Okay, DTFS of this equation, wherein since this part is basically not having anything related to n1, I can take this as a constant outside. Okay, so rest of the portion I will write inside the bracket. First let me write this little bit small so that I will get some gap here to write the equation within this page. So I write the same equation. I have split these two apart, and out of which the n naught portion I have taken, this portion I have taken it out and written it outside. So what is inside the bracket? Inside the bracket is basically the Fourier transform, the DTFS of x of n1, which I will write it as x of k, capital X of k, and what remains is into e raised to power minus jk omega naught n naught. Hence proved. So you can see that this is what we wanted to prove, that the DTFS of this one would be this, which we have proved. Next one. Next is the frequency shifting property, which basically says that if you are having a function x of n whose Fourier transform is x of capital X of k, then if you multiply x of n with a function e raised to power j capital M omega naught n, okay, if you multiply it with such a function, then the DTFS of that would come out to be capital X of k minus the m with which you have actually multiplied the x of n. So let us prove this. Its proof is very simple. If you try to take the DTFS, we know that the equation, based on the equation, it will be 1 by n naught, which is the period summation of n within the period n naught into e raised to power j capital M omega naught n small x of n multiplied with e raised to power minus j minus j k omega naught n. So I will try to join these two together. If I try to join these two together, what I will get is, so this is going to be equal to 1 by n naught summation n is within the period n naught, x of n is there, and now we are having e raised to power minus j omega naught n. I will write because here also omega naught n is common with this particular function, so that I will write common, and here you can see that it is plus m, so I should write minus k plus m, but minus is common here, so I will write k minus m. I will write k minus m. So what is this equation? This equation generally means that you are trying to convert a signal which is in n, with respect to n, you are trying to convert it not with respect to k but with respect to k minus m. So hence this equation is basically the Fourier transform equation, the Fourier series equation with the value of k now being k minus capital M. Hence proved. Next we will look at the fourth one. The conjugation property basically states that if you are having a function x of n whose Fourier DTFS is basically given by capital X of k, then if you want to find out what is the Fourier series or DTFS of the conjugate of x of n, all you have to take is the conjugate of x of capital X of k and flip it in the k axis. That means whatever is in the positive k, you make it into negative k, and whatever is in the negative k, you make it into positive k. The proof is quite simple. Let me use, okay, we know that the function x of k can be obtained by the equation 1 by n naught summation small n is within the period n naught x of n small x of n e raised to power minus j k omega naught n. If I want to take the conjugate of this, I will have to take the conjugate in the right hand side also, which I can get it as, so let me write it, x conjugate of k. Now n naught is a positive integer, so I can take that out. Summation n is equal to within the period n naught, and now we are having the conjugation appearing one inside, that is x conjugate of n, and then the conjugate of the e raised to power minus j k omega naught n terms, which comes out to be j e raised to power plus j k omega naught n. Okay, now if I put, instead of k I put minus k. Okay, if I put, instead of k, if I put minus k, then x conjugate of minus k is equal to 1 by n naught within the limits, n is within the limits within the period n naught, x conjugate of n e raised to power, now since I take minus k instead of k, I will get e raised to power minus j k omega naught n. Now what is this equation? This equation is the DTFS of which function? Conjugate of xn. Correct? And that is what we are having this, that the DTFS of conjugate of xn is x conjugate of minus k, which is given here. Hence this is proved. The time reversal property basically states that if you are having a function x of n whose DTFS comes out to be x of k, then if you want to take the DTFS of x of minus n, all you have to put it is minus k. That means it straight away goes for a flip. Let us prove this. We know that x of k, that means the Fourier discrete time Fourier series of any sequence x of n, is calculated by the equation 1 by n naught summation n within the period n naught x of n e raised to power minus j k omega naught n. Now suppose we put the value n is equal to minus n. Okay, therefore the limit will change, but again the limit will remain within the period itself. Okay, so I will not now write, I can write that therefore at n is equal to 0, m value will be equal to 0, and at n is equal to n naught minus 1, which is the upper limit, the value of m comes out to be minus of n naught plus 1. So again you can see that it's only going in the negative direction, that's all, but the range of values actually has a periodicity of n naught itself. So therefore I can write, now when I substitute that, I will write x of k is equal to 1 by n naught summation n is within the limit, but now I have changed n to m, so I will basically write this as m. Okay, m is within the limit of n naught itself. So the remaining part is, instead of n I will put x of minus m, and here also instead of n I will put e raised to power minus j k omega naught minus m. So if I put minus m, that minus and the minus in the front will become plus. Correct? That will become plus. Now if I am going to put, instead of k put minus k, instead of k put minus k, then what will happen? I will get, this equation is going to be, let me write it clearly, that it is going to be x of minus k is going to be equal to 1 by n naught summation m is equal to within the limit n naught x of minus m e raised to power, now since I am going to put instead of k minus k, so this becomes minus j k omega naught m. Instead of n we had already substituted m. Now what is this? This equation is with respect to m for a function x of minus m. So that means this is basically the DTFS of x of minus m. So this is basically equal to the DTFS of x of minus m, or I can write x of minus n. Now you will be thinking, why should I write n? Okay, m is just a name that we are giving, any variable. Okay, so hence the DTFS of a sequence whose time axis is flipped is the original frequency plot also getting flipped. Okay, hence proved. In time scaling, we will basically deal with expansion here. We are talking about the expansion, the discrete time signal expansion, which basically says that if you are scaling a function x of n, with a factor of m, it means that you are expanding the signal such that at all those places of the new signal, wherever you will have n to be a multiple of m, that means if n is multiple of m, okay, you will put the value x of n by m. Okay, and if suppose you are having at other places, you will put the value 0 elsewhere. Okay, that means suppose if I am having a value, let's say I am having x of n which is 1, 2, 1. Okay, then if I am trying to expand this, then I will use this formula. Suppose I am trying to expand this with a factor of 2. So I will write x of n with a scaling factor of 2. It means that I will have values x of n by 2 and at other places as 0 for those values where n is multiple of 2, okay, and 0 elsewhere. Okay, so this is the new n that I am trying to make. So the new n, suppose if I am going to write the time axis, I will write the time axis below, which is 0, 1, 2, 3, 4, and the negative axis, suppose -1, -2, -3, -4, like that. Okay, so this n is basically this one. So this is the new n. So wherever n is a multiple of 2, so you can see that 2 is a multiple of 2, 4 is a multiple of 2, similarly -2 is a multiple of 2, -4 is a multiple of 2. So at those values, even 0 I will write as such, I will write the value what is there here, which is 2 itself. Okay, now for n is equal to 1, so if I am trying to see n is equal to 1, 1 is not a multiple of 2, so since it's not a multiple of 2, I will put the value as 0 here. Next, n is equal to 2. N is equal to 2 is a multiple of 2. So I will put the value x of n by 2. What is n here? N is 2. So I will get x of 2 by 2. What is 2 by 2? 1. So what is x of 1? X of 1 is this value, which is 1. So I will put 1 here. Similarly, 3 is not going to be a multiple of 2. So I will put the value 0. 4 is a multiple of 2. So I will get x of 4 by 2, which is x of 2, but x of 2 there is no value here, so as such I will stop it here. Okay, similarly in the negative axis I will get 0, 1, no other value. So you can see what has happened basically when I scaled it with 2 is in between these values I have got 0. That's all that has happened. Okay, but for writing that we use this equation. According to the time scaling property, if we are having a function which is x of n scaled by m, then the DTFS of that will be we know x of k, but now that divided by m, and here the periodicity will change. Period is now going to be m times capital N naught. Why? Because here also the periodicity is changed. The period, here also the period is changed to m N naught. Okay, the proof of this one we will see later. Now why did I say that the period has changed? See, when I had a function 1, 2, 1, I expanded it to 1, 0, 2, 0, 1. So in effect what has happened is that the periodicity has actually increased. Before it was 3, now it is 6. Okay, now it is 6. So the period has basically changed. If the period of the time sequence changes, then obviously the period in the other side will also change, and that is what is reflected by writing that the period is m N naught. So we will see that proof later when we do tutorials. Okay, let us go to the next one, which is the multiplication property. States that if you are multiplying in time domain, then in the frequency domain it will be convolution. Okay, so let us try to prove that. We know that the DTFS is going to be given by 1 by N naught. Now since both the signals X and N are supposed to be having the same period N naught, we are having the period as N naught itself. Okay, so 1 by N naught, summation N is within the period N naught, and now the signal is X of N into Y of N e raised to power minus j k omega naught n. Now instead of y of n, I am going to substitute the value of y of n as its Fourier inverse transform. That means the inverse DTFS. That means I can write this as 1 by N naught summation N is equal to within the limit N naught X of N. I will use a different color here. Let me use blue. Instead of y of k, I am going to write the Fourier expansion of that, which is summation k is within the limit of period N naught y of k e raised to power j k omega naught n. Okay, so instead of y of n, I have substituted the inverse equation. That means y of n is basically can be found out by y of k. That equation I have written here. Okay, y of n can be found out by y of k. That equation of inverse DTFS I have written here. Now what remains in the other side is e raised to power minus j k omega naught n. Now changing the order of summation. So changing the order of summation, what I can do is I can take the k value outside. So summation, so I will write again using the color that I have used on top. So summation k is equal to within the limit N naught. Okay. Now since I will do one more thing, since it is a different, I will use a different variable. I will use L. Okay, because no other reason. The only reason is that since I am going to use the k again later, I will just use a different variable instead of L, because k already I have used here. So it is not good that I use k here again. So I have used it. I have used L. Okay. So based on that, I can write L is equal to within the period N naught. I will take the L values outside, which is y of L. Okay. And the remaining values I will take inside, which is summation of, which again I will have to use a different color. So I will use summation of n within the limit N naught. Okay, X of n, and these two I will combine, which comes out to be e raised to power minus j then k minus L omega naught n. Okay, now what is this much portion? This much portion is basically when taken with 1 by n naught, it comes out to be, so I will write that here. So summation L is equal to within the limit n naught y of L, and then 1 by n naught I will take inside the bracket now. So 1 by n naught summation n is equal to within the period n naught x of n e raised to power minus j k minus L omega naught n. Okay, there now the whole equation is same, the only difference is going to come at k minus L, isn't it? Instead of k it will be k minus L. So this is basically, now I am going to write the whole equation. Summation L is equal to within the period n naught y of L, and what remains here is basically the Fourier transform of x of n, which is x of, now instead of k I will write k minus L. And what is this? This is basically x of k convolution with x of k convolution with y of k. Okay, so this is proved, hence proved. Next is for periodic convolution. That means if I am having convolution in the time domain, then in the frequency domain it is as good as multiplying the two Fourier transform, the DTFS of x of n and y of n, and multiplying it with the period n naught. Let us try to prove it. We know that the DTFS equation is given by 1 by n naught summation n within the limits of n naught. We are having x of n convolution with y of n, okay, into e raised to power minus j k omega naught n. Now if I am going to substitute the value of the the convolution, I will get it as 1 by n naught summation n is equal to within the limit n naught. Now the summation value I will write using, the convolution value I will write using a different color, and I will use the variable r. Okay, I will use the variable r. So r, since this is periodic convolution, it will be for a period of n naught, x of r y of n minus r. This is the equation of convolution, okay, multiplied with the e raised to power minus j k omega naught n. Now changing the order of summation. That means I will take the r outside, so I will get 1 by n naught, so I take r outside, so summation r for the range of n naught x of r, okay, and then the remaining summation n is equal to within the period n naught, and what remains is y of n minus r, which I am going to again write in a change color, y of n minus r e raised to power minus j k omega naught n. Now if I am trying to put n minus r as a new variable p, therefore n can be written as p plus r. Suppose if I am going to substitute this above, I will get again 1 by n naught summation r within the limit of period n naught x of r, and now here the summation n for the period n naught y of n minus r can be written as p and e raised to power minus j k omega naught. N can be written as p plus r. This can be now split it up. That means I can take the r portion separately and attach it with this function. So I will get therefore this as 1 by n naught, and I will use the blue one, which is summation r is equal to within the period n naught x of r. And now if I split this, the r portion, if I am going to take out from here, I will attach it with this one, which is e raised to power minus j k omega naught r, and then the remaining portion I will again put it in summation n is equal to within the period n naught y of p e raised to power minus j k omega naught p. Okay. Now what I want to do is I want to multiply and divide with n naught. Okay, that I am doing extra. So I will mark it as an extra here, that it is n naught divided by n naught. Okay, if I am doing that, see what will you see? What do you see here? This is basically x of k, correct? Why? Because this is the DTFS of x of r, and this n naught, not the numerator. This n naught is basically 1 by n naught, and this function is basically the DTFS of y of p, which is y of k. Okay, and what remains? Only this n naught remains. So that these two multiplied with n naught, and that is what is basically the equation that we are having here. So using this simplification, let me write it here. So this is basically this n naught, this first n naught I will take outside. So n naught multiplied with this much portion is x of k, and the second this much portion is basically y of k, hence proved. Next is the Parseval's theorem or Parseval's identity, which is given as, if I try to take the energy of a periodic signal within one period, we all know that it is given by the equation magnitude of xn square summation. And what the Parseval's theorem says is that if you would try to take the energy of the xk, that means the DTFS, that would also become as the same. So it will be by just taking the summation within the limit n naught of x of k, let me write it properly, of x of capital X of k magnitude square. That is the Parseval's theorem. Let us prove it. Now for proving it, let's take the left hand side. The left hand side is 1 by n naught summation k is equal, not k, sorry, n is equal for the limit for the period n naught, and now x of n magnitude square can be written as x of n multiplied with x of n conjugate. Okay, so I can write this as x of n into x of n conjugate. Okay, now what is x of n? X of n is, I can write x of n itself. I can write x of n itself through its Fourier coefficient as x of k summation k is equal to within the period n naught e raised to power j omega k omega naught n, j k omega naught n, isn't it? So that is what I am going to do for this conjugate of xn. What I am going to do is I am going to rewrite this as 1 by n naught summation n is within the period n naught x of n, and now whatever is x of n, that I am going to write it here as summation, okay, k is equal to within the period n naught and then capital X of k e raised to power j k omega naught n conjugate. Okay, now if I try to take the conjugate inside, then basically I will write capital X of k instead of capital X of k. I will write capital X of conjugate of capital X of k, and instead of this I will write it as minus. Correct? I will write it as minus. If that is the case, then changing the order of summation, not basically changing the order of changing the order of summation, I will first write from k is limit n naught capital X conjugate k, and then the other portion I will write inside, which is 1 by n naught. Let me write 1 by n naught inside. Then summation n is within the limit period n naught xn e raised to power minus j k omega naught n. And what is this much portion? What is this much portion? This much portion is basically the conjugate of x of DTFS of x of n. So that I can write it as summation k is equal to, for the period n naught, x of conjugate k and multiplied with x of k. And what is this? This is basically the magnitude. So this is basically the magnitude of x of k. So I can write this as, I can write these two together as magnitude of x of k square. Hence proved.